I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the failure analysis of the weld joints. In this particular presentation, we will be talking about the failure analysis of weld joints related with the carbon steel components. Okay. So, the as far as content is concerned, initially we will be talking about the weld defects and their relevance with regard to the failure, and then carbon steels. What are the carbon steels? What are the different grades and how does it affect the different phases? And one typical parameter related with the steels is the carbon equivalent, which determines the hardenability of the steels and which in turn affect the weldability. So, we will try to see that how the hardenability and weldability are related. Then the weld metal and the HZ properties relate with the carbon steels and how they are affected. And then common issues with the carbon steel weld joints, then the case study on failure of the carbon steel weld joints, and then the failure analysis observations and the findings, related findings. Okay. So, as far as the common welding defects are concerned, you know that when the weld joint is defective, it can obviously lead to the failure of the weld joint very easily. Okay. So, efforts are made to make the weld joints free from the defects by choosing and by establishing the proper welding procedure, so that there is no defect. But still, if there are defects, then it will be reducing the load carrying capacity and the performance of the weld joint. The multiple types of the weld defects can be there, like porosity. Porosity is primarily caused by the improper cleaning of the base metal, or the moisture is in the electrode which is being used, improper shielding of the weld zone during the welding. Okay. So, if the welding is not done properly, cleaning is not done properly, surface preparation is not done properly, then it will lead to the porosity. Porosity may be in form of the like spherical shape family pores, which are indicating that these are the gaseous defects. Okay. When it is dendritic in morphology, then it is termed as the shrinkage porosity, due to the rapid cooling that is particularly observed. When the gases or atmospheric air present around the weld zone, then the molten metal interacts with the air, forms the certain compounds. Okay. So, there are two possibilities, like the metal is interacting with the impurities like sulfur, silicon and oxygen, nitrogen, and forming their oxides, nitrides, silicates, sulfides, etc. If these compounds which are being formed in the weld metal having the density similar to that of the metal, then they will get well distributed. But if they are of the lower density, then they will start floating and they will get segregated on its own, and or if they are heavier, then they will settle down. So, the most problematic inclusions are those where most problematic inclusions are caused by those compounds which are having the density similar to that of the metal, and that is why they will be well distributed in the weld metal. Okay. So, inclusions so whenever these are there, these break the metallic continuity and also act as a stress raiser. Okay. So, these are the two ways by which the inclusions adversely affects the performance: break the metallic continuity and act as a stress raiser. Okay. So, stress concentration will be high in those regions, and therefore, under the externally applied stresses, they will tend to promote the fracture, crack. So, where multiple types of the cracks are observed in the weld zone due to the unfavorable welding conditions, due to the improper use of the filler metal, improper use of preheat or the welding heat input. So, let us say underbeat cracking. This happens particularly when there are inclusions in the base metal, laminated inclusions in the base metal. When the solidification temperature is high due to the presence of impurities, it causes the solidification cracking. And when the hydrogen content is high, very high hardness is being produced due to the martensitic transformation coupled with the residual stresses, then it promotes the cold cracking. Okay. So, all these will be occurring due to the unfavorable welding procedure including use of filler metal, use of proper preheat, use of excessive, you can say, the restraint leading to the development of high residual stresses, or inclusions are there in the base metal itself leading to the underbead cracking. Too high bead angle. Okay. So, like there is a weld metal and the weld bead is developed with the very high bead angle like this. So, if the bead angle is too high, it will be causing the high stress concentration at the toe of the weld. Okay. So, improper bead angle, this may be, this is one form where bead angle is too high, or the unfilled section where the weld zone is not filled properly. So, there is an unfilled section leading to the reduction in cross sectional area in the weld zone, and that in turn will be reducing the load carrying capacity and strength of the joint. So, improper weld bead leads to the improper bead angle, and improper weld bead leads to the stress concentration or the unfilled section. That is the another kind of the improper weld bead. Then lack of fusion or lack of penetration. This is the case when the joint is made partially and a portion of the base metals is still left to be joined. So, that is the lack of penetration. When there is no proper fusion of the base metal, just metal is being placed over the surface of the base metal being welded without proper fusion with the base metal, that is the case of the lack of fusion. So, in that case, metallic bonding between the weld metal and the base metal is very limited, and that in turn reduces the strength of the joint. This is particularly observed when the heat input is less than the desired one. So, both lack of penetration and lack of fusion are primarily caused by the improper or limited heat input or lack of proper heat input. The next one is the very rough weld surface, means the placement of the weld metal in the desired position is not proper, or workmanship is very poor. In that case, it leads to the very rough weld surface, and the rough weld surface increases the stress concentration against the external loading, promotes the fracture, especially under the fatigue conditions, promotes the corrosion. Okay. So, this figure particularly shows that the pores inclusions and like say the iron needles, if there is iron impurities or nitrogen impurities leading to the iron nitride formation. So, multiple kind of the defects can occur. Whenever there is a defect, it reduces or adversely affects the mechanical performance of the weld joint, particularly due to the two reasons. One, it reduces the net load resisting cross sectional area. Okay. If the load resisting cross sectional area is reduced, then metal's ability to take up the load is reduced. Like say metal's ability to take up the load is sigma A, load resisting cross sectional area is reduced, then obviously the load carrying capacity is minimized. So, if the greater is the reduction in A, more will be the reduction in the load carrying capacity. This is one aspect. Another way by which the defects reduce the load carrying capacity is that these induce the stress concentration, these cause the stress concentration, means in a localized way in certain areas the stresses will be too high, and from those areas wherever these defects are present, high stress concentration will be promoting the cracking and so the fracture. Okay. This is what we can understand from this system. Like say there are two types of the defects. Okay. One is at the surface and another is at the center. So, say at the center we have the defect of twice A size, and at the surface defect size is A, and the crack tip radius, the defect tip radius is say rho, like this. Then how the maximum stress is being developed under the external stresses, that is what we can see. Like say due to the externally applied load P for a given cross sectional area A, nominal stress sigma naught is P by A. But when there is a defect, then how does it affect the stress concentration and maximum stresses? So, maximum stresses will be about equal to the twice of sigma naught multiplied by A. A is the defect size for the surfacial defect, and twice A for the internal defect, and the rho T is the rho t is the the crack tip radius. So, greater the size of defect and smaller is the crack tip radius. These two adversely affects the stress concentration, means these increase the stress concentration significantly and thereby promote the fracture. Okay. So, greater the A means greater the reduction in load resisting cross sectional area, and greater and sharper is the crack tip, means the greater will be the stress concentration. That is what we can also see, like the stress concentration in weld joints, when the bead angle is too high, then it causes the stress concentration at the toe of the weld, when the bead angle is too high. Okay, so the weld failures can also occur in those cases when there is no defect. The joint is sound, but like say a weld joint has been made, okay, but the selection of filler is improper. Weld metal which has been developed is of 300 MPa, while the base metal is of 500 MPa. So, during the service, if it is subjected to 400 MPa load, it will fail from the weld metal, which means the weld metal is weak and the weld will obviously fail. So, the low strength filler is one case, all the weld is sound, but the properties of the weld metal are not proper. Okay. The another possibility is this, where the heat effect, the HA jet formation is reducing the strength to a greater extent. Say the base metal is 500 MPa, both the sides, weld is also like say 550 MPa, but the HA jet properties have been compromised very badly due to the heat input, and its softening has taken place, and therefore, its strength has been reduced to 350 MPa. So, instead of the weld metal and base metal, HA jet failure will be taking place. Everything is fine, there is no sound, there is no defect, joint is sound, but still failure will occur from the HA jet. Another possibility of the failure, when the joint is sound, but still the failure can occur due to the hardening and embrittlement. This is the case when say this is the weld metal, it is sound. HAZ is also sound, no cracks whatsoever, but the properties have got altogether in such a combination that they do not serve the purpose. Like say the base metal toughness is 150 joules, both the sides, but the heat has modified the HAZ properties to 30 joules and weld metal properties to 10 joule. In this case, this kind of the weld metal will not survive the impact conditions and it will fail in very brittle manner catastrophically. So, the joint is sound, but the property degradation which has taken place due to the improper use of the welding procedure will lead to the compromised mechanical properties in terms of the excessive hardening or embrittlement of the weld metal or of the heat affected zone. Another problem which is encountered commonly in the weld joint of the dissimilar metal combinations, especially like say one side we have B, another side A, and really both these metals are not good metallurgically compatible, chemically compatible. So, when the fusion is done for developing the weld joint, because of the difference in composition and their compatibilities, it tends to segregate one side. Like say you will see segregation of certain elements at the fusion boundary. Okay. So, this is excess presence of certain elements near the fusion boundary is termed as unmixed zone. This unmixed zone formation reduces the corrosion resistance 1, sometimes increases the hardness and brittleness, okay, and in other areas where such kind of the alloying elements are not present, they will also be experiencing the drop in properties. Okay. So, this kind of the issue is particularly observed in during the fusion welding of the dissimilar metals having the limited or no metallurgical and chemical compatibility. Okay. So, this is the another issue which is observed. The joint may be sound, but the properties are such that they will be compromising with the joint performance. Then chemical and metallurgical heterogeneity, this is very common in all types of weld joints, we will never see the same set of properties as that of the base metal, whatever method of joining is applied, because the weld zone definitely will be showing the different set of properties than the heat affected zone and then the base metal. So, you have HAZ, uh, you have weld and you have base metal, both the sides. All three are going to show the different set of the microstructure and mechanical properties. So, if this variation in structure and properties is within the reasonable range, with reasonably acceptable range, then it is fine. But if these go beyond the acceptable range, then you see the performance is degraded heavily. But a weld joint usually have chemical and metallurgical heterogeneity, and which in turn leads to the reduced corrosion performance and non-uniformity in terms of the mechanical properties. Many times unfavorable metallurgical transformation also leads to the huge degradation in the joint properties. This is particularly observed with the transformation hardenable metals. It can also be observed in case of the precipitation hardenable, work hardenable and grain refined metals. And in all these cases, in transformation hardenable metals, there will be hardening, while in other metals there will be softening. Okay. And all this credit goes to the unfavorable metallurgical transformation. Okay. So, we need to take care of these undesirable metallurgical transformations by developing suitable welding procedure specifications, which will include proper cleaning, proper edge preparation, proper preheat, proper welding procedure, welding process, and then of course, the application of the heat using suitable choice of the, like say, the welding current I, V and S, and then post weld heat treatment or post treatment whatever is needed, so that we are able to realize the sound weld joint with the desired combination of the structure and properties. Okay. Now, many times you see, this was the one aspect where a lot of the soundness has been ensured, metallurgical properties have been ensured. But what if the design is not proper, which means we are developing the weld joint using certain kind of the materials. Okay. Say, let us understand this in this way. Say, these are the two set of the components. Okay. Edge has been prepared. So, in case of the thick sections, edges need to be prepared like this. Okay, like this, and this section has to be filled in. So, for filling in, what we are using, that is the part of design. Okay. This is applicable especially in case of the consumable welding processes, where suitable electrode or filler metal is used. So, what should be used for developing such kind of the weld joint? Okay. So, the weld metal properties need to be designed or and developed accordingly in such a way that we are able to have a weld joint which will perform for long as desired. Okay. So, we know that every weld joint is supposed to fail or designed in such a way that it resists the failure by the particular mechanism by which it is expected to fail. So, let us see it in this way. See, the weld joint will be used for certain applications. Application means there will be certain working conditions. In those working conditions, the joint will have the failure tendency to fail by certain mechanisms, and for registering the failure of the weld joint by those mechanisms, material should have certain set of mechanical or chemical properties. Okay. So, we need to develop the joint in such a way that it is, we use suitable filler or electrode in such a way that it offers you the desired set of properties. So, considering the application, we see the working conditions, and considering the working conditions, we try to find out what will be the failure mechanism, and considering the failure mechanism, we will identify which properties should be used so that it resists those failure mechanisms, and then accordingly we select the suitable filler metal. Okay. So, For a given application, if we know that the failure mechanism is ductile, fracture will occur in the ductile manner, then our design criteria should be the yield strength, like as per the type of load, tension or compression. If the failure mechanism is expected to be a brittle fracture, then we should see the fracture toughness, like say critical stress intensity factor, notch toughness, ductility and ductile to brittle transition temperature, depending upon the conditions on in which it is to be used. Say brittle fracture is taking place under the very low temperature conditions, then it will be the DBTT also. Then the fatigue, if the failure mechanism is expected is the fatigue, then we should consider the fatigue limit or fatigue strength with the stress radius or hardness. If it is thermal fatigue, then ductility and peak plastic strain. If the failure mechanism of the weld joint is expected to be creep, then the creep rate at a given temperature. If it is a plastic deformation, then the yield strength. And if the weld joint is expected to fail by the stress corrosion cracking, then we must see K1 SSC and resistance to the corrosion in specific environment. Okay. So, any issue in development or any difficulty in development of the proper welding procedure specifications or in design, then it will be leading to the development of the joint, which will have either defect or the weld joint may be without the defect, but will be there with the certain kind of the properties which are not suitable for the performance of the weld joint. Or if the weld joint has not been designed properly, if the design criteria is not proper, then also the failure of the weld joint can take place and it can happen in very premature manner. Now, we will talking about the carbon steels. So, the carbon steel is basically the alloy of iron and carbon with the residual elements like manganese, silicon, sulfur and phosphorus. Concentration of these is maintained well below the 0.05 to avoid the cracking tendency. These are the residual elements and not expected to contribute towards the mechanical properties much. So, in carbon steels it is the iron and carbon only. So, again based on the carbon content we have low carbon steels, medium carbon steels and high carbon steels, which is less than 0.25, 0.25 to 0.5, okay, and greater than 0.5% of the carbon. So, what happens when the carbon content in steel is increased? Increasing the carbon content in steel increases the perlite percentage, decreases the ferrite percentage, and beyond the eutectoid point we are able to see the cementite as the third phase. Okay. And what happens to the properties when the carbon content is increased? Our ductility comes down, toughness comes down, hardness keeps on increasing and tensile strength increases up to the eutectoid point and then it starts decreasing. Okay. So, this is about the properties. So, if the carbon content in steel say greater than 0.5, then what will happen? Like it will have the greater tendency during the welding. This is corresponding to the iron carbon diagram, but when the welding is done, you see increasing the carbon content increases the tendency of the formation of the perlite and martensite in the weld zone even in the autogeneous welding, and that in turn increases the cracking tendency, hardening and embrittlement of the weld joint. Okay. So, whenever if the carbon content in the steel is less than 0.4, then using suitable preheat it can be welded, moderate preheat it can be welded. If it is less than 0.2, then certainly the welding is easy like in most structural steels, but if it is 0.2 to 0.5, then it using suitable preheat it can be done very easily depending upon the thickness. And but if it is greater than 0.5, then that makes the welding difficult and that requires extra precautions in terms of not just preheat, to use of suitable filler metals, post weld heat treatment, etc. About these things we will be talking in detail now. So, carbon equivalent is one of the parameters which is very important from the welding point of view, because it affects, it determines the hardenability, how easily a metal can be hardened through the transformation of soft phases into the martensite. So, soft phases like ferrite, and perlite into the martensite, and this is and this carbon equivalent, what it is basically, the carbon equivalent is the percentage measuring the carbon content and the effect of other alloying elements similar to that of the carbon. Okay. So, if we see the most common equation for calculating the carbon equivalent as per the International Institute of Welding is like carbon plus Mn by 6 plus CrMO and vanadium divided by 5, means the weight percentage of these elements, and copper plus nickel divided by 15 for the weight percentage of the respective elements. So, what it gives us like Ce, carbon equivalent, according to this IIW, and similarly other equations also have been developed. This is another equation which considers the silicons as well. So, carbon equivalent according to the American Welding Society, carbon plus manganese plus silicon divided by 6, chromium, molybdenum, vanadium divided by 5, and copper, nickel divided by 15. Then this is the another equation which is about the carbon plus silicon divided by 30, Mn plus Cu plus Cr divided by 20, Ni divided by 6, Mo divided by 15, and V divided by 10, and 5 multiplied by boron. So, these three elements take care of the various constituents and different elements. Point is, carbon equivalent directly affects the hardenability, which in turns it affects the ease with which the soft phases can be converted into the martensite, and so the hardening of the steel can take place. Okay. So, but hardening, increased hardening in the welding means increased tendency of cracking, reduced toughness, okay, increased tendency of the cold cracking also. So, what is done if the carbon equivalent is like say less than 0.2, then steel can be welded without any difficulty. If the carbon equivalent is in the range of like say 0.2 to 0.7, then using suitable preheat the steels can be welded. But if the carbon equivalent is greater than 0.7, then steels are considered to be non-weldable. Okay. In carbon steels, of course, we will be using these first two components only, where we have carbon, silicon, manganese, other elements are the residual elements. So, ease of the welding to a great extent determined by the carbon equivalent, because higher the carbon equivalent, greater will be the hardening and embrittlement tendency and cracking tendency. Therefore, to avoid those tendencies, it will be required to use suitable preheat. Higher is the carbon equivalent, greater will be the preheat. So, there are certain equations, carbon equivalent in x axis and preheat temperature in y axis. So, the increasing carbon equivalent means increasing degree of preheat, like say 50 to 300 in terms of degree centigrade, with the increasing carbon equivalent 0.2 to 0.7. Okay. So, increasing carbon equivalent means increasing degree of preheat, and you know it is not easy to work with the carbon steel which is preheated to the 200 or 300 degree centigrade, because handling of the welding or welding of the preheated steel is difficult, and also it requires lot of resources. So, preheating can minimize the issues related with the high carbon equivalent in terms of the embrittlement and cracking and residual stresses also, but this is more difficult, and that is why the carbon steels with the carbon equivalent less than 0.5 can be welded using suitable preheat. Why all these things happen? That is what we will try to understand. Like say these two plates are being welded, and this is the suitable heat source. Here is the heat source. When heat source is passing through a particular point of interest which is close to the weld zone, and this is a little away from the weld zone, and if the temperature profile as a function of time is recorded, what we get? The point which is very close to the welds, the weld center line, that will be experiencing the higher heating rate, higher peak temperature and higher cooling rate, as compared to the another point B, which is located away from the weld center line, that will be experiencing the lower heating rate, lower peak temperature and the lower cooling rate. Okay. So, these are the three things of the great importance. Okay. One is the peak temperature, another is the cooling rate. Third thing that we can derive is what is the time above which a particular location remains above certain critical temperature. For example, if this is the temperature of our interest, then that how long a particular point remains above certain temperature. Okay. So, if we take say this temperature is say 700 degrees centigrade. So, the duration for which the point A is maintained above 700 degrees centigrade is this much, while the point B is maintained above 700 degrees centigrade for a shorter period. So, this determines the soaking time or the time of high temperature retention, that is shorter for the points which are located away from the weld center line. Okay. That is what we can see easily using this weld thermal cycle diagram. So, if the point is close to the weld center line, peak temperature is high, cooling rate is high. Okay. If the point of interest is located away from the weld center line, then the cooling rate is low and peak temperature is also low, and accordingly the soaking time is also short. Okay. These three things are very important from the transformation point of view, which will be taking place at these two locations. That is what we can see here from this diagram. The point 1, which is located close to the fusion boundary, experiences the heating cycle and cooling cycle like this. Those which are located away, they will be experiencing little lower heating rate, lower cooling rate and lower peak temperatures. Okay. Likewise 3.3. So, the peak temperature keeps on decreasing, and similarly the high temperature retention period will also keep on decreasing, and the cooling rate will also keep on decreasing on increasing the distance away from the fusion boundary. Okay. Why these are important? Like say initially the base metals will have what they will have, the soft phases. Carbon steel will have basically the ferrite and pearlite at the room temperature, like say this one. So, when it is heated, it remains so like ferrite and the pearlite until this temperature is achieved. Then pearlite transforms into the austenite, and then ferrite transforms into the austenite, and above this we get the complete austenitic state. So, the point must be heated to get the complete austenitic state for its transformation into the other phases like martensite or bainite as per the metal composition. In this case, it will be the martensite. Okay. So, if a particular point is heated above the upper critical temperature, then what will happen? It will have tendency to form the complete austenite. Otherwise, what will happen? It will be forming the ferrite and austenite, or below that it will not be doing anything, it will remain ferrite and pearlite only. So, all the zones which are heated above the lower critical temperature, they will be falling under the heat affected zone, while those which are below that, below the lower critical temperature, they will remain unaffected. So, they will behave like a base metal only. Okay. Now, how long that temperature is being maintained, that is another important thing. Okay. So, if the point is close to the boundary, temperature is high, it will be experiencing temperature much above the upper critical temperature also. If the temperature is high, so what is the importance of temperature and time? Soaking time. I was telling about the soaking time. If soaking time is short or long. So, for a soaking time determines whether the homogeneous austenite will be formed or not. Okay. So, here what it shows that temperature versus soaking time relationship in transforming the ferrite, pearlite and alloy carbides into the austenite. So, it passes through the number of stages as a function of time. Higher the temperature, shorter the time it takes to form the homogeneous austenitic state, and lower the temperature, greater the time it takes to reach the homogeneous austenitic state. So, if those points which are close to the fusion boundary, they will have greater tendency to form the homogeneous austenitic state, homogeneous austenite, while those which are away from, even if they have been heated above the upper critical temperature, but due to the low temperature, they will take longer time. So, it is possible they will reach either heterogeneous austenitic state or austenite with the ferrite and alloy carbides, or alpha ferrite plus austenite plus alloy carbide. So, like that. So, it can reach just to the intermediate stages. Okay. So, the complete Homogeneous austenitic state will not be achieved if the soaking time is short. This is what typically happens in case of the welding. What this diagram shows, like this is the weld zone. Here say this was in the molten condition, so obviously it will have the austenite which is completely homogeneous. The point close to this will also have the homogeneous austenitic state, but those which are away they may have the heterogeneous austenitic state or no change like this. So, those which are like the point in the weld zone will be experiencing the highest cooling rate. So, it will be forming the martensite only. The zones which are next to the fusion boundary will also be experiencing the very high cooling rate, which is good enough for the martensite transformation, but which are away from may be experiencing the intermediate zones or this zone as per the cooling rate, and accordingly it may form perlite and martensite or fine perlite. So, since we are going to have the variety of phases perlite plus martensite or perlite plus ferrite like this, since there are variety of the phases, so accordingly the properties are going to change. How? You see, next to the in the weld zone property hardness will be maximum, then it will be coming down like this. So, this is corresponds to the martensite, this is martensite plus perlite, and this is corresponding to the perlite, fine perlite and ferrite, and then base metal. Properties in terms of the hardness will keep on decreasing. So, maximum hardness will be achieved in the weld and in vicinity of the heat affected zone. Why? Because cooling rates are very high, and here austenite will be transforming into the martensite directly due to the rapid cooling. This is what we can understand. This is the relevance of the CCT diagram in the welding. This is what we can see. This is the fusion zone, say, of the steel. So, the zone which is next to the fusion boundary is subjected to the, say, in case of the very low carbon steels, it will be experiencing the partial melting zone. Then the next to that will be having the coarse grained heat affected zone, and this is the intercritical zone where it is being heated in the ferritic and austenitic state, that will be experiencing the fine grained heat affected zone. Then the recrystallization zone, the zone which is heated in above the 400 degree centigrade to the lower critical temperature, that will be recrystallized. So, that is the recrystallization zone and the base metal. So, during the welding, the different zones will be experiencing the different rise in temperatures, and accordingly the different zones will be formed. Heat affected zone is crucial, as I have already said. It should be narrow as possible, but it can be wide if the heat input is very high. HZ can be narrow, but or it can be narrow or wide, but it cannot be eliminated. So, efforts are always made to make it narrow, so that the undesirable effect of the heat in the HZ can be minimized. It is most of the time it is problematic. Why? Because due to the undesirable metallurgical transformation, it reduces the corrosion resistance, it frequently causes the softening or hardening as per the metal system, and with the transformation hardenable steels and the cast irons, it frequently causes the embrittlement and cracking tendency. Therefore, it requires the preheating. Okay. Preheating helps in reducing this embrittlement and the cracking tendency. If the heat input is increased, that is what we can see. We can do the welding with the 0.1 kilojoule per mm like in laser welding, or it can be 1 kilojoule per mm, okay, like in TIG welding, or it can be 5 kilojoule per mm in case of the submerged arc welding. So, if we keep on increasing the heat input, what will happen? Weld zone size will increase, HZ will increase. Okay. Weld area increases and the heat affected zone increases. Why? Because increasing the heat input makes the grains coarser because of the lower cooling rate, which will be experienced by the weld zone and the heat affected zone. Okay. So, this is what it shows. When the heat input is low, the cooling rate is high, high temperature retention period is short, grain coarsening is limited. But when the heat input is very high, cooling rate is low and high temperature retention is long, high temperature retention time is long. So, the grains are coarse. Okay. So, this is just a schematic to show that what happens in case of the transformation hardenable steels for those who in annealed condition or in QNT conditions, the behavior is entirely different. So, how the properties change actually in the weld zone, hardness is maximum, then little lower in the next the zone B, which is experiencing transformation hardening and grain growth, partial hardening and grain refinement in zone C, like this. So, the different zones will be experiencing the different D is for the recrystallization, partial hardening and grain refinement in zone C, and an unaffected base metal. What happens? So, this is the similar trend actually when the welding is done. In the normal case, like hardenable steel in annealed condition, it will showing this kind of trend only. But when the steel is welded in the Q&T condition, like steel has been hardened by quenching and then subjected to the tempering of say any temperature from 200 to 700 degrees centigrade. Then as soon as the temperature of the metal goes beyond this tempering temperature, the metal gets over tempered, and because of this over tempering, especially in the heat affected zone, it gets softened. This softening is attributed to the over tempering of the quenched and tempered steel. So, even not necessarily that HZ will get hardened, but it can get softened also, especially when the steel is being welded in Q and T conditions, quenched and tempered condition. Now, we will be talking about one case study. In this case study, the failure analysis of a machine component which is made of the carbon steel. So, a structural weld joint of the machine component made of the carbon steel, actually this machine component was subjected to the impact loading, okay, and component failed prematurely within the 2 months of the service catastrophically. So, sudden fracture occurred actually, and therefore, investigation was carried out to see like the component was made of the 1045 steel, and when the composition was checked, it was found as specified, but the weld metal composition was found higher than the specified ones as compared to the 0.25. Welding was done using the V groove, developing the V groove using without any preheat and use of 1.5 kilojoule per mm heat input. Design as per recommendation, and visual examination of the weld joint which failed showed the fracture from the weld zone with the flat fracture without any deformation. So, this is indicating the brittle fracture. Okay. So, means the weld is brittle, this is the one observation. Okay. And another one is the high carbon percentage, carbon content is higher than the recommended one in the weld metal. Further investigation when carried out showed that the weld strength 650 MPa as compared to that of the 4 MPa as recommended, and toughness was significantly lower than the one which was specified. Okay. So, high hardness, high strength, high carbon, so high carbon percentage and the reduced toughness. Okay. These were the two, and brittle fracture. Additionally, when the structure study was carried out, it showed the untempered martensite. This is the typical the behavior of the steel weld metal, that it shows the martensite only. So, the martensite, and no defect was found whatsoever, operation was normal, no maintenance requirement. So, the fracture surface when a studio and SAM was carried out, it shows the cleavage facets without any plastic deformation. When the weld joint was compared with the other one which did not fail or the new one, lower toughness, higher hardness and strength was observed, and also the carbon content was found high. So, it was concluded that the failure occurred due to the low toughness caused by under the impact condition caused by the absence of the suitable heat treatment. You see, if the steel was the weld joint was tempered, means subjected to the heat treatment, then it would have the tempered martensite with reasonably good toughness, and it would have showed some indications of the fracture with. So, the absence of the proper heat treatment, proper preheat and improper electrode as indicated by the weld metal composition showing the higher carbon content than the recommended one. So, that is all. Now, I will summarize this presentation. In this presentation, basically I have talked about the various types of the defects, so their causes and how the presence of defect leads to the failure. Okay, in what ways the presence of defects leads to the failure of the weld joint. Then I have talked about the various metallurgical aspects and the way by which the metallurgical changes in the weld joint affects the microstructure and mechanical properties, which in turn dictates the joint performance. I have taken also one case study, and wherein it was found that weld joint failed due to the low toughness, and that resulted due to the improper electrode and the improper preheat and the post weld heat treatment. Thank you for your attention.